Hi everybody, this is lesson 2 of the permutations and combinations chapter. We're looking at the fundamental counting principle, and in this lesson we're going to be looking at restrictions on the fundamental counting principle. When you're faced with a problem that has a restriction in it, the trick is to start with that restriction. There are two restrictions that you should know because it will be assumed that you will apply them without being instructed to do so. The first is that when you're organizing letters in a word, it will be assumed that you can't repeat the letters unless you're told that you can. The second is sort of the opposite. If you're dealing with the digits of a number, the assumption is that you can repeat the digits unless you're specifically told that you can't. Now let's take a look at an example. So how many three-letter words can be made from the letters in the word math? So this is an example of the fundamental counting principle. And notice in this case here that because I'm dealing with letters, the assumption is that I can't repeat them. So my subtasks for the fundamental counting principle are as follows here. I have got to choose 3 letters, so I have 3 subtasks. I have 4 choices for the first letter. Then I have 3 choices for the second letter. And for my last letter, I've only got 2 letters left to choose from, so I've got 2 choices for that last letter. To arrive at my solution, I simply multiply the number of options I have for each subtask together. Thus 4 times 3 times 2 equals 24. Now let's look at another example. How many 4-letter words can be made from the letters in the word theory if repetition is allowed? So this is an example of the fundamental counting principle, and as such I have to first consider the subtasks. And there are 4 of them. I have to choose 4 different letters. Each one is a subtask. But the group that I'm choosing from is a group of 6 letters, and because we're told that we can repeat them, we're always going to have a choice of 6 letters. And so the solution to this problem will be 6 multiplied by itself 4 times, 6 to the 4th, or 1296. Now let's take a look at a different example, this one using digits. How many 4-digit numbers can be made using the digits 3, 4, 5, 6, 7, and 8? Once again, I need to consider the subtasks in this problem, and there are 4 because I'm looking to find 4 digits. But because I'm looking at digits, and because I wasn't told otherwise, I can assume that these digits can be repeated. So because I have 6 to choose from, and I'm allowed to repeat, I will always have 6 to choose from. So like the previous question, the solution to this one is simply 6 to the 4th, or 1296. Now let's look at an example with an explicitly stated restriction. How many odd 4-digit numbers can be made from the digits 2, 3, 5, 8, and 9 if repetition is not allowed? To solve this problem, once again I need to consider the subtasks. Okay, and there are 4 of them because I need to choose 4 digits. But in this case, because of the explicitly stated restriction on the last digit, I need to start with that last digit. In order for the whole number to be odd, I need the last digit to be odd. And out of the group that I'm choosing from, there are only 3 digits that will give me an odd number. Because I'm not allowed to repeat digits, this leaves me with just 4 choices of digits for the first position. Then I have 3 options left over for the second position. And finally, there are 2 options for the third position. The resulting product is 72. Now let's take a look at a similar example with a slightly different restriction. How many 4-digit numbers greater than 3,000 can be made using the digits 0, 2, 3, 5, 6, and 8? To solve this problem, we first need to consider the number of subtasks that are available to us here. And because we're putting together a 4-digit number, there are 4 subtasks. The restriction here is that this number has to be greater than 3,000, which means that the initial restriction is on the first digit. Since 4 of the digits I can choose from are 3 or greater, there are 4 options for the first digit of this number. Now, because the question doesn't state otherwise, we can assume that we can repeat the digits. Thus, we're going to have 6 options for each of the remaining 3 digits in this number. The resulting product, 864, should be the total number of values greater than 3,000 that we can make from those digits. But this is not the correct answer. The problem is that in all the 864 numbers that we just created, there is one number where we chose 3 for the first digit, and then because we're allowed to repeat the digits, we chose 0, 0, 0. And that number 3000 is part of that group, but it is not greater than 3000, so it doesn't satisfy the restriction of the problem. 3000, however, is the only number that gives us that kind of problem. So if we just subtract 1 from the 864 numbers that we created to get 863, that will be the correct answer. Okay, now let's take a look at another example, and admittedly a kind of a hard one. How many even 5-digit numbers can be made without repetition using the digits 0, 2, 3, 4, 5, and 6? Seems pretty innocuous, but there's a bit of a trick to this. Once again, to solve a problem like this, using the fundamental counting principle, we need to identify the nature and number of the subtasks. Now, we're coming up with a 5-digit number, but it's going to be an even number, and so there's a restriction on that final digit, and that actually is what causes the problem here. For the number we're creating to be even, what we require is that the final digit be even. And that gives us 4 digits from our group that we can choose from for that final digit. But then the issue is, what do we do next? The problem here is the 0. If we choose a 0 to be in that final digit, then we have 5 choices for the first digit. Okay? Because it doesn't really matter, as long as the 0's been used, it doesn't matter what digit we start the number with. But if we don't choose a 0 for the final digit, we don't have 5 choices for the first digit because we can't choose 0 to start a number. So we actually only have 4 choices for that first digit. It must be non-zero. And so there's the problem. Is it 5 choices or 4 choices for the first digit? This causes a natural break in the problem. And the easiest way to figure out what to do is to do what I had suggested earlier on in this chapter here, and that is to talk through what your options are and listen to what you say. I need to create even numbers that either end in 0 or do not end in 0. Now the or in this case implies addition. So there are 2 scenarios here that we're going to add together. In the first scenario, we're going to have the number end in 0, and there is only one 0 to choose from. This leaves us with 5 choices of digit for the first position in the number. And then our number of choices progresses downward, 4, 3, and then 2. And these are the numbers that end in 0. Now we need to consider the set of numbers that we can create that are even, but don't end in 0. To accomplish this, we have 4 non-zero even digits that we can choose from that we can use as the last digit of our number. But this gives us a scenario where there's only 4 choices for the first digit, because in this set of numbers here, we cannot begin with 0, so 0 is not one of our options. Now this might seem a little odd, but we do have 4 choices for the second digit, because now 0 becomes an option that we can go to. And then we fill in the third and the fourth position with remaining 3 and 2 digits that we have to work with. And now finally we can conclude that there are 504 even numbers that we can create with those starting digits. For the final example that we're going to work through, we're going to look at how many numbers can be made from the digits 1, 3, 5, and 7 if the digits are not allowed to be repeated. The issue with this question is actually careful reading. It would be very easy to jump to the conclusion in this question when you're trying to figure out the number of subtasks that there are 4 digits that you're looking for. But that's actually something that you're assuming. The question never ever says how many digits are in the number that they're looking for. Now it could be a 4-digit number, in which case you'd have 4 options for the first digit, then 3 for the second, 2 for the third, and 1 for the fourth. Or it could be a 3-digit number with 4 choices for the first digit, then 3 choices for the second digit, and 2 choices for the third digit. Or it could be a 2-digit number with 4 choices for the first digit and 3 choices for the second digit. Or it could be a 1-digit number with just 4 options, giving us a total of 64 different numbers.